I think if you say it like that, they might sneeze on it before they give it to you.
Time to get back to it, Jeff?
Dude.
I was saying, why is math so time-consuming? That is the question.
I don't know. Why is building a boat so time?
No, why is math so? Why is math such a time-consuming? Everything else is just like, you do this, yay. Math is just like,
Oh, build a boat, done. Build a boat. Make a town, hey, we're done. Yeah. Divert a river, hey, look, it's done. Hey. I wish, right? It actually is just like everything else.
Here's an argument. I'm going to make a sandwich. X plus 2 equals this much of peanut butter mixed with jam to get the perfect balance
Exactly.
of jelly and peanut butter.
Exactly. Okay. Now, to be honest, math has been used to find the sweet point. Now, in America, we have, you put so much fat and salt and sugar, and there's certain points that the three things make the ultimate taste. And normally they put so much of something in, they got to put so much of the other thing in just to get it to that sweet spot.
Yeah.
So there's a whole lot of math behind that. That's at least a three-dimensional problem, right? Sugar, salt, fat, right? Anyway, we don't have to go there. Okay.
Are you going to give us the homework assignments at the end of class for each chapter?
I did put 12's homework assignment in there, didn't I?
No. It's
Oh.
That's 11.
All right, so what I'll do is I'll email you guys the updated homework sheet. I was hoping to do that this morning. I was hoping I had 12 up there, but now I guess not. I can go ahead and give you 12-1 when we get done lecturing. Yeah, because I can make it up right now.
So, do you think we're moving at a good pace? Like, are we like ahead of schedule or
No.
No, and you're slowing me down. All right, here we go. So we just talked about what an inverse function means. We talked about how it's used. We talked about the fact that we've used them before. We just didn't call them inverse functions. The very next thing that we'd be interested in is how do I find one of these things officially? Not just what does it look like on a picture, but what is the function itself, right? It has to be its own function. So, and I don't want to do something more complicated than just x plus 7, the inverse is x minus 7. That's too easy. Plus, it's not true to life. I mean, I'm going to have more complicated functions to work with. I want to know a general way of finding the inverse. So, how to find... And by the way, I used this notation just a minute ago. This is the official notation for inverse function. It does not mean 1 over the function. It doesn't mean reciprocal. They just chose this notation to mean inverse function. Right? So the inverse of x minus 1 is not 1 over x minus 1. That doesn't make sense. It should be x plus 1. So this does not mean reciprocate or flip over. That's not what it means. That symbol officially means the inverse function, the function that does the opposite stuff. So given f of x equals x cubed minus 5, for example. This is almost going to be too nice to believe. Does somebody remember if I had a graph of an inverse, a graph of a function, how do I graph the inverse? So let's all right, let's do it. You ready? Let's do an example like that again, and let's finish it out this time. This is really nice the way this works. All right. So let me see. Let's do this, and then this, and this, then this. Sure. So I have this function here. Why is that a function? Vertical line test is passed. Why does it have an inverse? Horizontal line test is passed. You with me? Some of you guys might realize that means that it always has to be going up or going down. If it ever goes up and then goes down, it's going to fail the horizontal line test. So it's got to be what's called monotonic. It's got to be monotone in direction. It's got to be always going up or always going down. It can't come back on itself. That's all a side note. Tell me, what's the collection of points this function goes through? What point is that?
-2, -4.
Mm-hmm.
Negative
Zero.
0, negative 1, 1, 3.
3, 4.
Good. Now, what points must the inverse go through then?
The opposite.
Zoom tight. The opposite, sure, but be more specific. It's got to go
2,
through what?
4.
No.
Negative 4, negative 2.
-4, -2. Remember, what's the inverse supposed to do? The function made -2 become -4. Do you see what I mean when I say that? It took -2 and made it become -4. The inverse is going to undo that. Right? It's like the antidote. It says you're -4. Oh, poof, you're back to -2 now. I undo what the other one did. So this one is going to go through the point -4, -2.
-1, 0.
-1, 0.
3, 1.
3, 1.
4, 3.
4, 3. Now watch what always happens. This is really kind of kick-ass. If you plot those points, we will have plotted the inverse function without even knowing what the functions are, which is still unsatisfactory, which is why we're going to make an algebraic way to do it, not just a visual way. I want to know what the shit the function is. But how do I graph this? -4, -2. Plop. -1, 0. 3, 1. 4, 3. Does anyone see any symmetry here at all? Is there any symmetry here in any way? Any symmetry there? Any like mirror reflection?
Yes.
Now this does some funky stuff and it goes through the mirror, but oh well. There would be a mirror.
It's like DNA.
Yeah, I like that. Right, DNA is some freaky alien stuff, but still, they found some new letters for DNA, by the way. It's really interesting. Anyway, look that shit up.
Oh, hell no.
Anybody know what this line is?
The axis of symmetry.
No, sure, but this is the line y equals x. If I flip the x and y, the function flips over the y equals x line. So you're always going to get these nifty-ass Nazca line-looking things. Nazca line. Another thing to Google if you don't know what the hell that is.
So if it's an inverse thing, will there always be like a little intersection? Will they
Only if, do you see, if I didn't make that blue line go over the y equals x line, there would have been no crossing over.
Okay.
Right? So I could, if I would have made it do this, there would have just been a pure mirror image over there. But why did it cross over? Because that blue line crossed over, so the black line's got to cross over also.
Okay.
Just a little interesting side note. Yes?
So, the -1 just means to switch them, right?
Yes, so the inverse function, that means inverse, not reciprocal. It means inverse function, and that means that whatever the original function did, this new function, this inverse function, will undo it.
Like mirror it?
Totally. Around the y equals x line. So yeah, you just flip the x and y. It's almost too beautiful to believe. So whatever the function does to this, the inverse function takes the answer that was there and takes it back to where it started. That's what it does. That's the visual. Now let's talk about the actual, how do I create a function? How do I know this has an inverse? Because it looks like this. And so it passes the horizontal line test. Okay, so if it's squared, would it have an inverse? No, because it's going to look like that or like this. No, it doesn't pass the horizontal line. Oh, shit. Okay, all right. So given this, I know I want to, what do I do to find the inverse? I switch the x and y. Stay with me now, right? I switch the x and y. So where's y? Bring y back. I'm bringing y back. Where's the y?
The negative sign.
This is the y, isn't it? That's what we just replaced y with f of x a while back. We can bring it back if we want to. Is that a huge thing? Okay, good. All right. So the look on the faces is keep going, not what the shit did you just do. Now, what did I do visually? I switched X and Y. So what do I do here? I always draw this little line to say I'm not doing something algebraic. I'm actually applying an idea. I switch the X and Y. And now you solve for Y. Do you see how by doing this, when I go to solve for Y, I'm going to undo all the operations that are there. So I'll end up with a function that has all the opposite operations in it. Doesn't that sound like what the inverse function should be? If I start to solve this, what am I going to do first? Solve it for Y. Add 5. Isn't that the opposite of what this did? So add 5. I get x plus 5 equals y cubed. And then what's the next step?
Wouldn't x be negative x? Because you moved it over?
Okay, okay. This line here means I'm applying an idea. That's the only reason I draw that little line is because I don't like to pretend like I actually moved things. I applied an idea. I switched the x and y. Can I do that legally, algebraically? No, you can't just go, I want the x over here. No. But what am I doing? I'm trying to find a new function. And what's the steps to do it? Switch the x and y. That's not something like algebraic. You can't just do this anytime you want to in an equation when you're trying to solve an equation. But what am I trying to do? I'm trying to find an inverse. So that means I want to switch the x and y. I didn't subtract x. Because then it would have been minus x cubed. I'm not solving for y already because it's already solved for y up here. So I switch them. Bam! Whatever the x is happening, I put a y there. And wherever the y is, I put an x there. And now if I solve for y, I'm going to do all the opposite shit in the opposite order. If I do all the opposite things in the opposite order, that should be what we call the inverse function, the opposite function. So what does this function do? Subtracts 5. Okay, this one adds 5. And how do I finish this? How to get y by itself? What do I do to both sides to get y by itself?
Square root.
Take a cube root. So I get cube root of x plus 5 equals y, but I'm going to put f inverse now because that's what that really is. That's the inverse function. What does this function do to an input first? If I said, what's f of 2, you would put a 2 there. What's the first thing you would do? You would raise it to the third power. What's the last thing this function does? Cube roots it. Opposite. What's the next thing this one does? Subtracts 5. What's the first thing this does? Adds 5. They are inverse functions. Visually, how do you get the inverse? Switch the x and y and graph it. Algebraically, how do you get the inverse? Switch the x and y and solve it. Oh, that kicks so much ass. Because that's the basic idea of inverse. It switches the x's and y's. You guys still hate that, but that's really it. So here. Do that one. Well, that's yours. It's all yours. Plus me there. Okay. So if you'll notice on the thing I just gave to you, this is 12.1 part 2, because inverses are also in 12.1. There's the 4 steps. Replace f of x with y, or h of x, whatever it is. Replace that with y. Then you switch the x and y. Then you solve for y. So what's the first step to solve for y? Subtract 1. Then you, how do you undo a fifth root? No.
Cube it.
No.
To the 50.
To the fifth it. I like it. Raise it to the 5th power. Yeah, they're minus 1. So those kill each other. So you get x minus 1 to the 5th. This is what I mean. Don't do this shit. Don't write that 5 times and go in some. Just leave it like this. Please, 3 hot. Equals what?
Y
Y minus 7. So the last thing is? Add 7. So you get f inverse is x minus 1 to the 5th plus 7. So let's check this out. Does this make sense? What's the first thing this guy does to an input? What's the first thing he does? If I put 8 in here, what's the first thing I'm going to do to 8?
8 subtract 7.
I'm going to subtract 7. What's the last thing this guy does?
Add
Add
7.
7.
What's the next thing this guy does? 5th root. What's the next thing this guy does? What's the second thing in the middle? The 5th power. What's the last thing this guy does? Add 1. What's the first thing this guy does? Subtract 1. Everything's opposite. So of course that's the inverse function. This process only makes sense. This goes along with what I said. Every time we've solved an equation, we're applying inverses. So if I do this and solve this equation, I'm applying all the inverses to everything that's there. So I end up with the inverse function. It does all the shit in the reverse order. Okay, maybe. So if I graphed this and this on the same graph, they would have the symmetry we saw earlier always. That's just a fact. It's going to have a mirror right at the y equals x line. It's going to have a mirror. So if this one does this, the other one's going to do what it is to this or something. It's going to have to be symmetric. And they really come out looking nifty sometimes. Okay. So go ahead and do those couple things here. Number 1 and number 2 right there. Find those inverses. Just to get some more practice. Yes.
So when you put it to the 5th power, it kills the square root sign and...
It kills the 5th root sign.
Okay.
Sure.
Okay.
Yeah. So that is a single sign. 5th root and the 5th power kill each other.
Okay.
So yeah, it's only a square root if there's no root there. It's understood too. Bless you. Okay. Bless you. So if I bring y back, then I do what?
Then you just add...
No.
You switch it. No, you switch.
Switch the x and y. I really don't know if you understand why I do that. You don't have to do this if you don't want to. Just for me, I have to do it. Because there's no way I can get from here to here. There's no legal way to do that. I'm applying a process that requires me to do this. Now, every step I take from now on is legal, right? I'm going to add 4 to both sides. So that's legal, and so forth. So I'm able to take care of this in one step. Multiply by the reciprocal. Because it's divided by 3, so multiply by 3. It's multiplied by 2, so divide by 2. Both sides. Die. So I get 3 halves x plus 4 equals, what was it, f? Yeah, f inverse. If you wanted to, you could distribute that. So you would, if you wanted to, that'd be 3 halves x plus 2 goes into 4 twice, times 3 is 6. So if you got either one of those answers, it would be okay. Yes?
So basically you're just solving it, but you just change the x and the y?
That's it. I love it when a student's like, why didn't you just say that? I'm like, I did. But I explained why it works. And then I said that. All right, what about number 2? What's that? So y equals x plus 4 cubed. What's the first thing I do after I switch the x and y? No, definitely can't subtract 4.
Cube.
I want you to realize there is no 4 on this side. I have to cube y plus 4 to see what I have, so I really don't want to do that. I want to kill the cube so I don't have to do it. So I cube root. So we get cube root of x equals y plus 4. Subtract 4. Now it's free. It's not trapped in something, it's free. So I can subtract it. Cube root of x minus 4 equals y, but I'm going to replace that with
X.
what symbol? No.
No, the
F inverse. F is this. I just found the inverse of that to be this. Pop. Yes.
What if, like on the test, what if you accidentally put cube root x minus 4 equals y? What if you actually do that?
Oh, I don't know. I probably just put a note.
Okay.
You really should call it what it is. I mean, you brought y back in the middle.
Yes.
You should bring back the right notation at the end.
Okay.
Because you want to show the relationship between this and the f that was started off.
So if you cube 4 instead of killing it, would that still make it wrong?
Oh, hell yeah. What do you mean? I'm not sure. Do what now?
The first step when you kill the cube,
Yes.
if you cube the whole equation out, the y and the 4.
I want you to understand how that would be so horrific, because if right here you cube this thing, if you cube it out, meaning you multiply it, you mean like write this like this? Is that what you mean?
No, if you just did, if you just 4 times 4 times 4, and you put y to the third plus whatever that is.
Definitely not.
That's not the right order of operation.
This is very different from this. Very different. Very, very different. We should know that, because factoring cubes is not this easy. Not because math people want to make it hard, but because they don't work. That's all. It just don't work.
I wish it did.
Cubes are not based on addition, so they will not play well with addition. You can't just distribute the cube. You cannot, because cubes are not based on addition. That's the only reason. That's it. Cubes are based on multiplication. If it was 4y to the cube, I like that, then I could distribute that cube all day, because then it's multiplication. Cube goes, I know that, and it can go distribute. Here it's like, what the shit is this? Oh, cube doesn't know. Got to write it 3 times. So yes, that would be wrong. Okay. Here's a funky example, and then we'll move on. There's a really easy example of a function who is its own inverse. You understand what I'm asking? A function that is its own inverse. The easy example of this is y equals x. So if I have f of x equals x, and then I switch the x and y. It's its own inverse. Do you guys see that? Then f inverse would be equal x. Why does that make sense? Because what does everything do? It flips over the y equals x line. That is the y equals x line. Flip. Okay, it's the same thing. That's just an interesting side note. There is another function, a really simple function that is its own inverse that you wouldn't think that way of it at first. I'll show you. It's really neat. So here, you guys figure out the inverse function for this. Just do the steps. You already know what's supposed to happen, because I just told you. It's its own inverse. Don't force it. Just do the steps. Just to make it easy to look at. Okay, so make this y equals 1 over x. Then you switch the x and y. Now how do you solve for y? What sucks about y? It's on the bottom. So how do you take care of it? Multiply. xy equals 1. Now how do you get y by itself? Divide by? What the shit? Now what does the 1 over x function do? If I put a 2 in, what's f of 2? What's f of 2? 1 over 2, 1 half. What's f of 3? Isn't this the reciprocal function? This is the flip function? This is the flip function. So if I take a number and flip it, how do I undo that? I flip it again, right? So that only makes sense. This is the flip function. How do I undo a flip? I flip it back. That's why it's its own. Another reason why it's its own function is because it looks like this, and that already is, when I flip it, it goes right back on top of itself. So that's another reason why it's its own inverse, because visually it's already symmetric to the y equals x line. It just flips right on back on itself. Do you have to know that going in? No. I just wanted to show you a freaky example. All the steps just happen the way they always would. You don't have to know that ahead of time. Okay. Oh, here. Here's some nice examples finally. On the back, can you do those top two? Try those out. We did a few examples of that on the board earlier. Just graph, on top of those functions, graph their inverses. Why do they have inverses? Does everybody see what I'm talking about? The sheet we were just working on? Turn it over. And then on the top, I'm asking you to graph some inverses. Cool? Why do they have inverses? Why do those functions have inverses?
1 to 1.
They're 1 to 1. Why are they 1 to 1?
Because they have 1 output.
They pass the
Horizontal
line test. Beautiful. So if on a test I say why does this have an inverse, and you say because it's 1 to 1, that's not good enough because you haven't told me why it's 1 to 1 yet. Don't just say it's 1 to 1. Well, you haven't told me why. Because it passes horizontal lines. Oh, beautiful. That's why. So do it. Graph those inverses. I can graph those inverses in 1.
Okay.
Yeah, okay. I can look at that. It's supposed to be on 3. I'm not trying to be tricky with those. Believe it or not. Math teachers capable of not being tricky. Okay. All right, I like it. So here's this line. It's supposed to be a straight line. How do I graph its inverse? Well, it goes to the point -1, 5, -5. So what's the inverse going to go through? -5, -1, so negative, -5, -1, pop. It also goes through the point. You have to find every point. You're just going to find a few. Like 3 is plenty. It's a line. So I got 0, -2, so the inverse is going to go through -2, 0, like pop. And then finally I picked out 2, 4, it looks like. So the inverse is going to go through 4, 2. So 4, 2, pop. So here's the inverse. Make these big, make this big, make this big. So it's symmetric around the y equals x, like it's supposed to be.
Do we have to show that word on the bottom? Or do we just
No, I mean, I'm just doing it so you see where things are coming from, but you should be able to pick out the points. Now, if I were you, I would probably do this for myself so I don't get things twisted in my head. But if you don't write it down, you're not going to lose points. Now, the other one is a little more interesting. So it's got -5, -4. It's got -3, 0. It's got 2, 1. And then it's got, where'd it go? 3, 5. So what's the inverse going to go through? -4, -5. 0 and -3. 1, 2. 5, 3. I like it. So -4, -5. So we go -4, 1, 2, 3, 4. -5. Pop. That's that mirror image there. 0, -3. That's that mirror image there. 1, 2. That mirror image there. And 5, 3. Oh, it should connect those. That one's interesting, little bug with some antenna. Or not. All it is little body, giant legs. Okay, that's pretty good, right? Okay. Is that cool, guys? And so it's really nice that if, no matter if it's a graph or a function that I want you to find the inverse of, you do the same thing. You switch the x and y. Right? That's the same first step in both things. It kicks so much ass. All right, so we're going to apply this idea that I just told you about. Every time you learn a new function from here on out, we must also learn its inverse. So we're going to learn a new function right now, and then we're going to learn its inverse, and then I'm going to call it a day. You're like, that's almost a good idea, Jeff. You should just do that last step sooner. No. Is everybody cool with this?
Yes.
Okay. Like, make everything that, Jeff, please. Can't do that. That would be a major disservice to you. So, this might not be new to everybody. If you've seen logarithms before, you especially should have seen what we're about to do. And the way I normally have to teach this sounds a little weird, but we put x almost everywhere so far. We put it in the bottom, we put it as a base, we put it as a, just with a number. Right? I mean, we put x in all these different places. The one place we haven't put x yet is as the exponent itself, right? So what I mean is something like this. So here, I want you to, is this on there? Yeah. Let me give you, so it's right below the problems we just did. This is section 12.2. That's the function we're looking at, 2 to the x. Let me give you the x inputs because you started to make a table of values. This function is completely unknown to us so far. That is the one time you definitely make an xy table. So you have no freaking clue what it looks like officially yet. So let me give you a few things to try out. These are the 5 basic ones I do. When I hit a function, I'm not sure what it looks like. There's not many of those left for me, but there's still some. So I do these 0, some negatives, some positives, to see what the function does in those situations. So you finish this out. So for example, just to make sure everybody understands what's happening, when I put negative 2 in, what do I get? 2
1 over 4.
to the negative 2, right? I put a negative 2 like I always do. And then I just solve what I've just written. Negative power means flip. 2 squared is 4. I like it. Keep going. Not surprising, we're going to graph it when you're done with that. I don't know why I went all the way around. Too bad. So, I mean, if you work on this sheet, you got the graph right there for you ready, right? You don't have to make your own graph.